This is the next video in the series on advanced theories of bonding. We are talking about molecular orbital theory, and we just learned all about orbital overlap to form sigma bonds. So now we're going to move on to the quite less strong overlap to form pi bonds. So you might remember some of the pictures we drew for options of orbital overlap that could form pi bonding. One of those pictures we drew was to overlap two p orbitals that are parallel to each other. Now we used p orbitals in the sigma bonding section. Those were the px orbitals, and those are very special because the lobes lie along the internuclear axis. But for the py and the pz orbitals, the nodes do not lie along the internuclear axis. They are perpendicular to it. And so we're going to go ahead and do the py overlap and the pz overlap at the same time. So we have py and py look like this, and then 90 degrees from that is the pz orbital. So I usually draw it sort of like this to show some of the depth. Hopefully it's somewhat clear what that's supposed to be and not just like a large lumpy circle. And that's going to be the overlap of our pz orbitals in phase and out of phase. Okay, so let's start with the py overlap. Remember that when we have p orbitals, there is an angular node along the internuclear axis. So there's no electron density here. And as we move over the axis, we need to change phase. So for our in-phase mixing, we're going to make sure that the lobes of the same phase lie next to each other so that they can overlap. I didn't draw them very close together today because I was tired of how sloppy my pictures looked in the last unit. But trust me when I say that these are closer together and that there is overlap between these two lobes and these two lobes. Okay, so when we put these in the molecular orbital machine, what comes out is a pi bond. Remember that we characterized pi bonds as bonds that had electron density on opposite sides of the internuclear axis. So it's going to look kind of like a hot dog bun, is the easiest way to describe it. And the hot dog bun is going to have two phases, one plus and one minus. So that node is still there. Down the middle, there is still no electron density here, and that's how we know that this is a pi bond, because there's no overlap on the internuclear axis. But this looks like it is encouraging and strengthening to a bond, so we'll call this a bonding orbital. Now for our other option, if we have an out-of-phase overlap, where we purposely mix these in such a way that the positive and the negative phase lobes are overlapping with each other, we are going to have destructive interference when we go through the molecular orbital machine. So not only are we going to have that angular node down the middle that we always have, we are going to create a new node straight down the middle of the molecule, exactly where we wish a bond would be. And as for the orbital lobes, they look a little bit silly. Basically, they are pointing as far away from the other atom as they can stand to get, with the same color shading as before. So as you can see, hopefully from this picture, this is filling this type of an orbital weakens a bond. You're putting electrons far away from the other atom. And since the overlap happens on opposite sides of the internuclear axis, this is going to be a pi star orbital. And because it is not contributing to a bond, creating a node down the middle, this is an anti-bonding orbital. We're going to wait to draw the molecular orbital diagram until we do PZ, because we're going to put them in the same picture. So just hold your horses on that one. So for PZ orbitals, remember, even though they look weird in the way that I've drawn them on their side, they are still the same shape as PY. They have just been turned 90 degrees, and they're coming towards you, coming towards the camera like that. So they still have a node along the internuclear axis. It's just a little harder to draw now, but it's still there. And each of the orbital lobes changes phase as we move across that node. And so when we do in-phase mixing, we're going to purposely line up the orbital lobes so that the same phases are overlapping. So we're going to put the black lobes next to each other and the green lobes next to each other. And when we put this through the orbital mixing machine, we are going to get the same hot dog bun. It's just going to be 90 degrees on its side. So it's going to look sort of like this with a little bit of depth thrown in. So exact same shape, just tilted 90 degrees. So these two pi orbitals don't touch each other because one of them is on the y-axis and one of them is on the z-axis. So you can actually have two pi bonds in one molecule at the same time, which is how we form a triple bond. And again, the overlap here is on opposite sides of the internuclear axis. So we do have a bond here. I guess we can draw that in this one too. We have a pi bonding orbital. And then for our out of phase hybridization, we're going to purposely orient the orbitals so that we have the opposite phases overlapping with each other. The black phase and the green phase overlap, and the green phase and the black phase overlap. When we put those into the molecular orbital machine, what comes out is the same goofy butterfly shape with the new node down the middle, just tilted 90 degrees to make it almost impossible to draw. So we're still going to have this new node down the middle, although I probably should have drawn that with some depth, so that was my bad. Oh well, we'll deal with it. And our orbitals are going to look something like this. A little bit skinnier and longer than they were before, which may or may not be clear from the picture. And with the same shading, trying to point as far away as possible. So just picture this nice drawing of a pi star orbital and picture it rotated 90 degrees. That's what that picture should look like in your notes. So that is an anti-bonding orbital because there's a node right down the middle, and a pi because that overlap occurs on opposite sides of the internuclear axis. So we form an anti-bonding orbital. So now we're ready to draw our energy diagram. And we're going to include both of these. And the reason we're going to include both is because the pi orbitals for both of these pairs and the pi star orbitals for each of these pairs have the same energy, because they're literally overlaps of the same shape, just turned 90 degrees on their side. So the process is the same. So when we form two molecular orbitals, we have, or four molecular orbitals, I guess, we have pi orbitals made from py and a pi orbital made from the pz overlap. And we have a pi star orbital made from the py overlap and a pi star orbital made from the pz overlap. These are our MOs. And then along the side, we'll put our atomic orbitals. It's going to get a little cramped, but we can do it. So remember, the py and the pz orbitals have the same energy in a particular atom. So we can draw those at the same line and at the same value over here. So that this is our py and pz, and py and pz on this atom. And then we need to add our dash lines to indicate which atoms, which orbitals are overlapping. So even though it's just the py and the py and not both, we just can draw a line from the same point at the end here. So the py's overlap to form bonding and an anti-bonding, and the pz's overlap to form bonding and anti-bonding. So we have 2 and 2 in this case. 2 bonding and 2 anti-bonding form from the other 2 types of p orbitals. So I'm going to throw one last bit of information here at the end, since we talked about sigma bonding, pi bonding, and non-bonding. I'll show you what a non-bonding orbital overlap looks like. We don't need to worry about those at this point in our history into molecular orbitals, but just to complete the story and tie up the loose ends, here is what one looks like. So one of the examples we drew in a previous lecture of a non-bonding interaction was when we mix two p orbitals together that don't lie along the same axis. So for example, if we had the py orbital and the px orbital, they are lovely orbitals. They have the same energy. So energy-wise, they would be a great fit to form a bonding and anti-bonding orbital, but none of these lobes point at any others. We are a little bit out of focus here. There we go. So this orbital points along the y-axis, and this orbital points along the x-axis. So this is not going to lead to a useful bonding interaction or an unuseful bonding interaction. It just leads to no bonding interaction. So our molecular orbitals are going to look exactly the same as the atomic orbitals that we started with. We said that all valence orbitals are mixed together to form molecular orbitals, so these are still molecular orbitals. They're just molecular orbitals that are exactly the same looking as the atomic orbitals that they started with. And there's no contribution to a bond whatsoever, so these are called NBOs, which is for non-bonding orbitals. We only see these in more advanced, more complicated molecular orbital diagrams. Important to note, the shape is the same as it started. So the shape of the molecular orbitals that are formed here is the same shape as the atomic orbitals that were used to form them. And if we were to draw an energy diagram, which in advanced level situations we would say, here is a py orbital for this atom, and here is a px orbital for another atom, which are the same energy, so in that respect are a good match, but they do not have good shape overlap. So we're going to draw them here at the exact same energy that they started. And we're going to draw this one on the left only connecting to one atom, and this one on the right only connecting to one atom. So both of these are going to be non-bonding orbitals. So each of these atoms, each of these molecular orbitals has the same energy as the atomic orbital that it was formed from. But non-bonding orbitals don't contribute to bonding. It's just there. Sometimes they hold lone pairs, sometimes they're empty. They're just kind of there, not getting in the way, not causing problems. So that is everything you need to know about drawing pictures of constructive and destructive orbital overlap to form bonding and anti-bonding molecular orbitals. In the next set of videos, we'll talk about why molecular orbital theory is useful and what kind of information we can get from it.